Okay, welcome to week 6, day 1, where we're talking about big O notation and algorithmic efficiency. So forget these for now. We'll go through that later. But obviously, you guys have written functions before. You've written functions ranging from things that print out hello, comma, the name of someone that's input, to functions that calculate optimal change, to the Fibonacci sequence, to all this other stuff. Now, functions that we've written are, for the most part, relatively simple. You might disagree with me because you guys just came off of assessment 2, which was not that simple. But in comparison to many functions that do exist, it's still relatively simple. Later on, as we start dealing with big data sets, as we start getting into operations that require you to go through your data multiple times, your code is not just going to get longer in terms of the amount of lines that it has, but also longer in terms of the amount of time that it takes to run. So usually when we're programming, there's a couple of things that we like to do. The most, like when we're re-examining or evaluating our code. Number one is we want to make sure that our code is simple. So this is where, I mean, you guys have gone through refactoring exercises before. That's the first half of it, is you want to make sure that when you're reading through an old version of your code, that you can rework it and make it run, make it look better, make it maybe more efficient or effective than before. How do you judge efficiency? Number one, if it can do the same thing in a smaller number of lines, that's great. If you can do the same thing in a shorter amount of time, that's also great. The second thing that you want to do is you want to generally reduce the complexity of your function, which is where a big O notation comes in handy. So I think we talked about this back probably in like week 2 or 3, how you never want to, you want to avoid nesting loops as much as possible. Do you guys remember this discussion? Kind of? Yeah.
I
Well,
don't. I thought you wanted to nest loops.
well, if you can get something done with one for loop versus getting it done with a for loop inside a for loop inside a for loop, generally you want to get it done with one for loop instead of the one inside the other inside the other. The number one, the reason for that is because nesting 3 for loops is going to introduce more places where things could fail or you could have errors. Number two is that massively expands the amount of time and computing resources that your computer uses when trying to execute. So today's lecture on big O notation is going to be a bit of a high-level overview to learn about how we can identify how complex or efficient a program is by looking at it from essentially a for loop perspective and trying to learn about how we can simplify our programs. So big O notation is a way to essentially say how the runtime of a program scales with the size of its inputs. So for example, let's say I give you a list of 5 things and I tell you sort this list. Is that going to take a longer or a shorter amount of time than if I give you a list of 500 things? Please tell me it's going to take a shorter amount of time. Okay, great. Yeah. So ideally, right? But here's the thing. How much longer does it take you to sort a list of 500 objects than 5 objects? Does it take you twice as long? Does it take you 200 times as long? Because the answer to that is a very, very, very important answer. So you can design a code, right? You can design some code on your computer that's made to that you can test it with 5, 10, 50, 100 different uh, inputs. But you should know what's going to happen when you take your code that's running locally and put it on, say, your company's supercomputer. That that is not handling 5 or 20 inputs. That thing is handling a million inputs. And your code, you need to be able to know if your code can run well when it takes a million inputs or not. is you're probably going to have shareholders or other users saying, all right, how long is your code going to take to sort through these million inputs and do what I need to do on them? The only way that you can really figure out that answer in advance is by doing the sort of big O notation analysis. So what big O notation does is you take your function and you basically try to see based on how the function is structured, what type of relationship the function's runtime has with the amount of data that it takes in. Does that make sense? Any questions about the purpose of big O notation?
Sounds
Okay.
groovy.
Okay, so we'll walk through some examples. That way you guys can see why it's useful. So the best case scenario is something called constant time. So essentially, like it says here, if you pass in one argument or a million arguments, the code runs in the same amount of time. So why would this function be constant time? Anyone want to offer an explanation?
Yes, because it's only running once. You're checking the first element in an array, so no matter if an array is composed of one element or 1,000, it's still only gonna run that function or run the instruction in that function one time.
Perfect. Yeah, it knows what element to hit. It's gonna hit it and it's gonna return. You don't need to iterate through any. You don't need to go through any. So because of that, it's in constant time. We'll contrast this with linear time, which is where the runtime will grow linearly based on what you pass in. So someone other than Cisco for this one, since you just answered, why is this function in linear time compared to the other one being in constant time? I'll give you a hint.
For loops?
Okay, elaborate on that.
No, thank you.
Okay, fair enough. I'll just have to call on someone then. Or Art if you're fine.
Sorry. Sorry.
Oh yeah, it just looks like in this for loop, I'm starting to read for loops as like if every item is equal to value. So the it's just like it's going to look through all the values instead of going directly to the one that you want it to check. So it's just a little bit more time consuming.
Right. So in this case, think about the absolute worst case scenario. The worst case scenario for this function is if the value is all the way at the end of your array. So let's say I give you the numbers 1 through 10, and I want you to check if 10 is in that data set. You have to go, all right, 1 is not 10, 2 is not 10, 3 is not 10, 4 is not 10, da 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 da. Okay, fine, 10 equals 10. So how many times did we run through the loop? 10. So I ran through the loop 10 times for an array with 10 values. Now let's expand it. Let's say that we have something that has the numbers 1 through 100. And now I want to find the thing lying at the 100th element of the list. So the first element isn't that, the second element isn't that, the third element isn't that, the 99th element isn't that, the 100th element, okay, it is that. How many times do we go through the loop? 100 times. I went through it 100 times for something that includes 100 elements. So in the worst case scenario, you are going to go through the loop as many times as you have elements. So there's a one-to-one relationship, if you will, between the size of your list and the amount of time it takes to run through your function. Does that make sense? Any questions about that? All right. So Joe, I want you to tackle this one since you said for loops for the last one. Why is this one in quadratic time? It does come down to for loops.
Um, I don't know, but I mean, the difference here is that we have an empty list and we're appending to that list. So,
So just look at these two lines. So the only thing we're trying to figure out
okay.
is how many times we run through the for loops.
So this one has a nested for loop. Um, but otherwise, no, I'm not tracking on what we're doing here.
Okay, so let's say that, let me fill out my annotation. Let's say that array, oh, no, I can't spell. Okay. Array is going to be, let's say 1, 2, 3, 4, 5. So this is 5 things. No. Oh, sorry, Adam. Yeah, go ahead.
I was just wondering, could you define quadratic time for me?
Sure. So there's actually, let me see if I can. Hopefully this helps. There's also a nice graph around here somewhere that I don't have on me right now. But what it basically means is if you make the input, say, twice as long, or twice as much data, it's going to take 4 times as long to run through everything. Whereas for linear time, if you make it twice as long the input, and it take twice as much time to run through. All right, yeah, go ahead.
I wanted to take a shot at the quadratic time.
Okay, go for it.
Like I've seen situations like this before, like we have number one, number two, you're looking for the X and the Y coordinates. So like the first loop is going to go through the whole array looking for the X, and then it's going to go through again, all looking for that Y. So that's why it's because you have that nested loop, it's taking twice as long.
Okay, walk me through that again a little bit more slowly. I think you have most of the idea, but let's go step by step.
Well, I was comparing this to something we've seen in the past where we were looking for some X and Y coordinates. And so when the first for loop is going to find that X, and once it finds that X, after it goes through all of the array, then it has to go back through all of the array again to find that second coordinate, say that Y, or here, or in this case, number 2. So it takes twice as long because you're going through all the full array twice for the first loop and the second loop to find 2 different parameters.
Okay, so what you're saying is that it would take twice as long, or would be is it would take twice as long would be correct if they were not nested. So if I understand correctly, what you're saying is it would be something like for X in array, do stuff or Y in array. Is that roughly what you're saying, Art?
Yes, yes. And so I'm thinking there's a way that you can pull both numbers or both, like say the X or the Y coordinate in one trip through the array. Whereas like when you have it set up like this, it takes twice as long because you're running through the away array.
So it does take longer, but is it twice as long or is it even more than that? So let's run through an example. So let's say that my array here is 1, 2, and 3. So let's start with the innermost loop. How many times do we go through the array in number 2?
Go through it 3 times.
3 times, right? Why? Because we have 1, 2, 3 things in the array. So this one runs through it 3 times. However, we are running through the array 3 times every time we do this step. And how many times are we doing this step up here?
You're doing that one. Go ahead, Joe.
3, right?
3. Yep. So every time we run through number 1, or we run number 1 through the array, we have to run number 2 3 times. So the total number of times that we are running through the array here is 3 times 3, which becomes 9 times. How long is our array? Our array is 3 thingamabobs long. So for 3, again, this is very qualitative. So for length equals 3, we have number of times looped is 9. So now let's try this for a different array. Let's say that now array is 1, 2, 3, 4, 5. Let's do the same thing again. Let's start all the way at the innermost for loop and work up. So how many times do we iterate number 2? Someone who's not Cisco or Joe.
5 times.
5 times. Okay. And then what about number 1?
Looks like 5 also.
5 also. Right? Because we're just iterating through the same array. So every time we iterate, every time we enter this loop, we're automatically running 5 times. So 5 times 5 makes it 25. So we then have, if the length equals 5, number of times looping through array total is 25. So this is where that quadratic part comes in handy. Quadratic is just a fancy word for squared. 3 squared is 9, 4 squared is 16, 5 squared is 25. So if I had an array that was 100 elements long, how many times would we be looping through the array?
1,000.
Not 1,000. Close.
10th.
10,000. Yep. 100 squared. So this is the value of big O notation, is it lets you predict, number one, how many times you can loop through something, but also how long it can take. So let's do an example. Right. So let me clear all my drawings. And yes, math in public is fun. That's why I'm here.
I call it math for Marines too. The most simple numbers, and you're like, wait a minute, is that correct? Sorry.
I think it's the effect of all the crayons, but
Yeah, a lot of crayon consumption.
so let's go back to that length equals 3 example. So let's say for length is 3, let's say that it takes us 90 seconds to run through this code. Based on that, so we want to figure out how long it's going to take us to run through the code for, let's just do 10 seconds. Or length is 10. We want to figure out how many seconds it's going to take us to run through this code. Again, I know the mental math is not the most fun, but how can we break this down based on what we just talked about? Anyone want to give it a shot? So let's start off with the information that we know. So we know that for an array of length 3, it takes us 90 seconds to complete whatever we're doing, right? To complete running the function. How many times are we looping through the array for an array length of 3?
9 times.
9 times. All right. So length is 3, so we have 9 times is going to be 90 seconds. So how long does it take us to go through the array 1 time?
10 seconds.
10 seconds. There we go. Okay. So let's move this guy down. Now, if we have something that is 10, an array with 10 things in it, how many times are we going to loop through the array? Someone other than Joe.
100.
100. So we're going to loop through it 100 times. Now, how long does it take us per time? 10 seconds. So how long, time-wise, should it take us to do this for a array that is 10 things long?
1,000 seconds.
1,000. Perfect. There we go. It's at a 0. All right. So 1,000 seconds. Think about this as, of course, sort of similar to you're plugging away on code on your terminal, and where you can time how long 90 seconds takes. 90 seconds is not a long time, you know? And so I can run this piece of code with a very tiny array on my computer and say, aha, okay, this is going to take 90 seconds. Easy peasy. 1,000 seconds is a pretty long time. You don't want to be running that on your computer. If, let's say, your boss says, all right, look, I know you've been designing this little algorithm. That's great and wonderful. You're only running it for these really tiny data sets, though. I want you to tell me and make sure to tell me how long it takes to run on a big data set. That's exactly where big O notation comes in handy. If you can tell me how long it takes to run on a small data set, and I know if the time is linear or quadratic or logarithmic or something like that, I can plug in a bigger number into a timer function, and I'll basically predict for me how long it takes to run. So that's like the biggest benefit of big O notation. Okay, so let me ask you guys this. Which of these is the best? Is constant time the best? Is linear time the best? Or is quadratic time the best? And why?
Constant time, because it's faster and takes less time to run.
If I pass in like a list that is 5 things long, it takes 30 seconds. If I pass a list that's 5 million things long, it takes 30 seconds.
Mhm.
In this case, if I pass in a list that's 5 things long, it can take 5 seconds. Great. If I pass in something that's 5 million things long, it takes 5 million seconds. That's not so great. The quadratic time, if I pass in something that's 5 things long, it'll take 25 seconds. That's okay. If I pass in something that's 5 million things long, I don't want to know how long it's going to take to run because that's 5 million squared. Big number. We don't want something to run that long. Your computer will probably, fry itself out by then. So that's the reason, again, quadratic time and big O notation becomes really important when you're dealing with really big data sets, which we will get to later. But for now, it's sort of a good use of time for algorithmic practice. So don't worry too much about hashes right now. The main things to focus on are number 2, avoid nested loops, because nested loops are what gets you going from linear time to quadratic time, or to cubic time, or quartic time, or something else that has a big, like, n to the 5th power. You don't want that. That's all because you nest your loops. So avoid nesting your loops if you can. Also, if you find yourself writing code that has poor big O complexity, in other words, nested loops, try to refactor it to remove the nested loops to make it more efficient. Any questions?
Well, knowing this now, I think you would really cringe at my assessment.
I am now terrified, but thankfully, I'm not the one grading them. So if Jordan watches this recording, I think he'll know what to expect.
So I have a quick question on this. So
Yes.
essentially, we would in our code we would write in a function to handle this to kind of so that it'll spit out like, hey, this is generally how long it's going to take. That's how we would employ this, or is that correct, or am I off
Yes.
base?
So
Okay.
here, let me just Google this real quick so I can remember. Have you guys heard of the Python time library before?
Like if you import time,
Yes.
yeah.
So that's basically what you can use to determine to help you figure out big O notation stuff. So the first thing you want to do is just like we did, you read your piece of code and then you say, okay, how many times am I looping through? That tells you what your big O notation is. Then to figure out how long it takes to run your function, that's where you use the time module. and use the time module sort of like a stopwatch. You can run time.time before your function, run your function, and run time.time after. And then you subtract those two, and that'll tell you how long it took to run your function. You can do that for varying sizes of inputs, and then that'll tell you how much or how your function's runtime is scaling. Does that make sense? Kind of?
Yeah, I think so. So would you, but so you do this for each function though, or just at the beginning and the end? Because I thought it would be just like one time, but from what you just said now, it sounded like it was for per function.
So big O notation is something that applies like function to function. So
Okay.
let's write something random right now. Random function that takes in array input. So let's say let's make this like really no. Let's say for IDX in array input or IDX2 in array input. Plus IDX2, say thing. And then we'll just go down here and we'll just like return. So based on what we just saw, what type of algorithmic efficiency does this function have?
Quadratic.
Quadratic. Why quadratic? Because you got two nested for loops. Now, how can we prove that? So that's where the time.time comes in handy. So we could say something like start time is going to be time.time. And you run your function with, let's say, so this thing is 5 units long. And then we say end time is going to be time.time. We'll print out end time minus start time. So what this is going to do is this will give us that sort of that. Remember the practice problem that we did where I said, well, the length is 3 and it takes 90 seconds to run, blah, blah, blah. This does effectively the same thing. This says, all right, the difference between my end and start time is when I click my stopwatch on and off. That tells me how long it took my function to run. So if we run this real quick, we see that it for something with 5 elements, it took 1.9 times 10 to the minus 6 seconds. So let's make this array a lot longer. 4, 5, 6, 7, 8, 9, 10. This array now has 50 things in it. So if it's fifth, so let's write this down. So we have actually let me copy this and paste this down here, just so I can show you guys what I mean. So this will be runtime for n equals 5, and we'll stringify that. That should go. And we'll do the exact same thing now, but we'll say that this is the runtime for n equals 50. So because it's quadratic time, should be quadratic time, that should be a string. How long do we think it'll take to run with 50 things versus 5? How much longer? Remember, this is quadratic time.
Wasn't it 10 times as long?
So why would it be 10 times as long? Talk me through it.
I just thought that was like the definition of quadratic time.
So
It,
oh, go ahead, Art.
it should be whatever 50 squared is.
Right. So yeah, it'll be that squared long. Or more specifically, in this case, it'll be 50 divided by 5, which is 10 squared. So it'll be 100 times as long is how long it should take. So let's run this and see if that actually is the case. So what do we see here? We see for n equals 5, it's this tiny number for n equals 50, well, that's not exactly 100 times as large. It's more like between 10 and 20. Does that mean that this thing is actually linear time? No. Big O notation only works really well for really large inputs. For small inputs, everything kind of blends together. So, but Joe, to answer your question, this is sort of how we use the time module in order to time how long your function takes to run. Does that make sense?
Yeah, I think so. So when we use this, if we're calculating compute, is this sort of how we would look at that, or is that something totally different here? I'm just trying to wrap my head around when else we would apply this necessarily.
The main use case for big O notation and stuff like this is either, again, you're trying to predict how long it's going to take to run something on a far larger data set, or you're trying to, let's say that I give you two functions. I give you function A and function B. They both do the same thing. Now, which one? Now it's your choice. Do you want to use function A or use function B? How can you decide between them? You want to see which function uses less memory, which in
Yep.
Python is not really a concern, or which function takes less time to run. So that's the other sort of usage of it.
Got it. Yeah, that makes sense.
Awesome. Any other questions? All right, yeah, go ahead.
I hope I don't confuse a class, but we had a class on linear comprehension, I think it was. Um, and I thought that was allowing us to avoid multiple or nested for loops. So is it through line comprehension that could take us from quadratic to linear?
Are you referring to list comprehensions?
Yes, list comprehension.
So unfortunately, not really. List comprehensions are for loops. They're just compressed. So it's a for loop, but just put in a nicer, smaller format. So just to make sure, what you're suggesting, what you're referencing is something like, let's say if we have like array one is gonna, and then you say array two is going to be like x times 2 for x in array. Like, is that what you're referring to? All right, when you say list comprehensions?
Yeah, so it was kind of just like putting things in a neat little package. And I guess I didn't understand that we were still using for loops, or maybe we were using less for loops. But I thought that was going to help us speed things up.
So dot append. So this piece of code from 33 to 35 is functionally identical to line 31. So again, and you can also see that there is a for inside of your list comprehension. Excuse me. So list comprehensions are just condensed, shrunken for loops. That's all. So even if you include a list comprehension inside of a for loop, you're pretty much still nesting for loops.
Okay, thank you.
Yep. Anything else, or we call it for lecture today? Okay.